Hello all. So let us start with Unit 4, and the topic what we are going to discuss today is the first topic, General Object Detection Framework. So in this unit we will be talking about object detection. So far we have discussed about image classification. Before moving on to the topic, let us have a quick look on the topics of Unit 4. In the first part we talked different object detection terminologies and what is a different framework involved in object detection, and apply that framework with these models which are used for object detection. The first one is region-based convolutional neural networks. Second one is SSD, single shot detector, and YOLO, that is you only look once. These are the networks which are used for detecting the objects within a given image. In the next part we will talk about segmentation and also auto encoders. So this is the first part where we will discuss the first section, that is object detection framework. Then we will move on to these three networks which are used for object detection. Before moving on to what object detection is and discussing the framework of object detection, let us first understand how image classification is different from that of object detection. So far in the previous all the three units what we have discussed is different deep neural network models for classification of the images, where we assumed that there is only one target object in the image. But there might be situations where we will be interested in multiple target in the image, that is image given with number of targets as shown here, and we are interested to find these multiple targets. So we want to not only classify these images within targets within the images, but also we will be interested to find the specific positions within the object, that is we are localizing the targets present in the image. In computer vision, this process of classifying as well as localizing is called as object detection. So object detection is what? Not only classifies the target but also finds the position of the target within the image, that is localization. So this image clearly gives the difference, where in image classification the output, what do we get in image classification? The probability of that given image belonging to cat. If 80%, that means 80% probability of the given image belonging to cat. Whereas in object detection, what kind of outputs you get? You get two outputs. One output you get it as coordinates of the bounding boxes. The boxes what you see here for each target in the image are called as bounding boxes. I'll tell you what these bounding boxes are. So in the output of object detection, the first part what you get is coordinates of the bounding boxes. So how many I have here? 1, 2, 3, 4. So I will get 4 coordinates. In the first coordinate, I will have x, y, w and h of the first box. For example, this is my first box. Second output what I get is the same values x, y, w and h for the second box, third box and fourth box respectively. Along with these coordinates, the other output what you get is the predicted classes. So what are the classes which are predicted in the given example here? 2 cats, 1 duck and 1 dog. This is what called as object detection. Now what is this x, y, w and h? For example, this is your bounding box. The midpoint of this box, their corresponding values of x and y are called as the top left values, that is x and y, and the width and height of this bounding box is represented by w and h, which is called as the bottom right points of this given bounding boxes. Hope you have understood the difference. This table gives a clear picture of what image classification is and how is it different from object detection. The goal in image classification is to predict the type or class of an object in an image. And what kind of input we give? We give an image as an input with a single object, and the output will be the class label, or it contains the probability of the given image belonging to that particular class. Coming to the object detection, here the goal is to predict the location of the objects in an image through bounding boxes and also find the classes of the located objects. So here what is the input? Input is image here, but with one or more objects, and the output will be bounding boxes with the coordinates and class labels for each bounding box. Example, for an image with 2 objects, as I have 2 objects in the image, we will have 2 boundary boxes. bounding boxes. The first bounding box represented by XWH, its class probability. Second bounding box represented by the same coordinates of the corresponding box XYWH and its class probability. And I told you what is X, Y, W and H. X and Y represents the midpoints of the bounding boxes, the X and Y corresponding values. W and H represents the width and height of that given bounding box. Hope you have understood the difference. Now let us start with the general object detection framework. Before we discuss different networks which are used for object detection like RNN, SSD and YOLO, let us first have a clear idea, that is the structural idea of how these networks can be used for object detection, which is called as framework, general object detection framework. So it has four components. The first component is region proposal. The second component is feature extraction and network predictions. Third one is non-maximum suppression, and coming to the fourth you have evaluation metrics. So you will have all these four components. Once you understand these four components, you will apply these ideas what you have learned in learning these networks which are used for object detection. So the first one is region proposal. So let us discuss each component one after the other. Region proposal. In this, the system looks at the image and proposes ROI, that is region of interest, for further analysis. Now what are these region of interest? This is an image. You can see many number of bounding boxes. These are the region of interest which the model has given as the output from the first block called as region proposal. For a given image, it will generate n number of boundary boxes called as region of interest. And what is this region of interest? This is the region which a model expects that the object is present in that box. And region of interest, each boundary boxes are represented by a parameter called as objectness score. So you can see here all the boxes will have objectness score. This parameter objectness score will tell you the probability of that object contained in that bounding box. So if you can see here, this is the background bounding box which has low objectness score because very less probability of object contained in this bounding box, whereas the objects contained in this bounding box probability is more, that means it has high objectness score. So this n number of bounding boxes, that is region of interest, will be generated, and whose objectness score is high, only those boxes will be further passed to the next block, and these low objectness score bounding boxes will be abandoned, that is they will be suppressed. So what is region of proposal? Region of proposal will generate n number of bounding boxes with high objectness score and send it to the second compartment for the next further analysis. What is the second component which is found in the framework? Feature extraction and network predictions. Here visual features of the each bounding box will be extracted and we will find out the predictions of that given target within an image. So it has two predictions. Bounding box prediction, as I told you in the previous session, each object detection has two outputs. One is the coordinates of the bounding box called as bounding box prediction, represented by X, Y, W and H. And the second output is the class prediction, which will predict that detected target belongs to which class. This is what happens in the second compartment or the second component. Now, thousands of regions are proposed. Each object will always have multiple bounding boxes surrounding it with the correct classification. For example, this was the image given. I told you that one or more targets can be contained in the image for object detection. So in region proposal, it will generate what? It will generate region of interest with high objectness score. So objectness score is the probability that that bounding box contains target within that highest probability. So all these bounding boxes were found to have high objectness score. So these bounding boxes were passed to the feature extraction component where it will generate the coordinates of each bounding box as well as the class labels of each bounding box. Now what do you notice here is I have around 5 bounding boxes but only one target present here. So what my model will think that it has 5 dogs here. So what output I get? 5 dogs as the output, though only one dog is present, because I have n number of boundary boxes surrounding only one target. So in such cases, what do? Is we go for the third component called as non-maximum suppression, where the boundary boxes which are not required will be suppressed and the boundary boxes which involves the target only will be passed for further analysis. So one of the problems of an object detection algorithm is that it may find multiple detections of the same object. So instead of creating only one bounding box around the object, it draws multiple boxes for the same object. So this non-maximum suppression is a technique that makes sure that the detection algorithm detects each object only once. So the main aim of this NMS technique is to reduce the bounding boxes and convert those 5 or 6 bounding boxes to only single bounding box when we have only one target available. Now how will it do that? It has to follow few steps to perform this algorithm. The first step is discard all the bounding boxes that have predictions less than a certain threshold called as confidence threshold. So we will select some threshold value and we will find out the threshold value of these bounding boxes. If the threshold value or the confidence score of these bounding boxes is very less, then those bounding box will be suppressed. This threshold value is tunable. Depending upon the task, we can tune this threshold value called as confidence threshold value, which means a box will be suppressed if the prediction probability is less than the set threshold. So let us understand the steps involved in suppressing the bounding boxes in NMS algorithm numerically. So consider that we have 4 bounding boxes A, B, C, D, and A with confidence score 0.9. Now what do you mean by 0.9 as the confidence score? The model has a confidence that 90%, it is 90% confident that that bounding box has target within it. In this bounding box B, the model is 80% confident that object or target is present in that bounding box. 70% confidence and 60% confidence. These are the confidence squares of all these 4 boxes and these are the coordinates X, Y, W and H. Now let us assume the confidence threshold as 0.5 and IOU threshold as 0.5. I will tell about these parameters in the next slides. So what we are talking about, confidence threshold value. So we will find out the confidence threshold of a bounding box. If that confidence threshold is less than we will find out the confidence score of the bounding box, and if that confidence score is less than the threshold value, that is less than 0.5, that bounding box will be suppressed. If it is more than 0.5, then that bounding boxes will be retained. Now the first step involved is using the confidence threshold value to suppress or to retain the bounding boxes. As you can see here, all the 4 bounding boxes have confidence scores greater than 0.5. So none of the bounding boxes will be suppressed. That is, we will retain all the bounding boxes here. Coming to the second step. Now as all the boxes are retained, that is what all bounding boxes are retained, we will select bounding box with highest probability. Now among all these A, B, C and D, you can see here the confidence square is highest for A compared to the rest 3. So what we will do is we will select box A with highest confidence score as 0.2. That is, we will take box A as our reference bounding box. This is my second step. Coming to the third step, we will calculate how much that A is overlapping with B, C and D respectively, taking this bounding box as my baseline model. I will find out how much overlap is of A with B and how much overlap is between A and C and how much overlap is between A and D, so that we will be able to retain only those bounding boxes whose probability of having object or target within that is high. So what we will do for calculating that overlapping, we use a metric called as intersection over union. IOU is used to calculate the overlap of A with respect to B, overlap of A with respect to C, and overlap of A with respect to D. This is the formula to calculate IOU, intersection over union, area of intersection by area of union. First let us solve the numerator. Now, first we will find out a overlap between A and B. First find the area of A. How do we find the area? The top left values, that is the values of A are 1, 1, 4 and 4. So the top left values are 1, 1 and bottom right values of 4, 4. We find the area as 4 minus 1 into 4 minus 1, which is equal to 9. Similarly, we will find the area of B. B coordinates are 2, 2, 5, 5. Area is 5 minus 2 into 5 minus 2, which is again 9. We got the area of A and B. Now what is this numerator is, that is area of intersection is. For example, this is my A bounding box, this is my B bounding box. In the numerator, we are finding out the area of intersection. So this is the intersection of A and B. We will find area of this intersection. So to find area of this intersection, first we will calculate area of A, then we will calculate area of B, and then we calculate the area of intersection. So to calculate the area of intersection, this is also in the form of a bounding box. How can I find area of this? In the same formula. So first I need to find out the coordinates of this bounding box. So to have coordinates, that is you need to find out the value of x, y, w and h, top left points and the bottom right points. To find the top left points, this is the formula. Maximum values of the top left of A and B. So top left of 1, 1 and 2, 2. Maximum value is among 1 and 2. 2 is the maximum value. Among 1 and 2, 2 is the maximum value. So the top left values are 2, 2. That is x and y is 2, 2 for this area. Coming to calculating the bottom right values, that is w and h, the formula is minimum of bottom right coordinates of A and B. So bottom right coordinates are 4, 4 and 5, 5. Minimum of 4 and 5 is 4. Minimum of 4 and 5 is 4. So I get w and h value as 4, 4. So these are the coordinates of what? This area. And to find the area of this intersection, 4 minus 2 into 4 minus 2, which is equal to 4. So my numerator value what I got is 4. Coming to area of union, formula to calculate area of union is area of A plus area of B minus area of intersection. So area of A is what? 9. Area of B is what? 9. Minus area of intersection is 4. So 9 plus 9 minus 4 is equal to 14. So numerator is 4, denominator 14. You will get 0.286 as your intersection over union. That is 28% of overlap is between A and B. Similarly, we will try to calculate the overlap of A with respect to C and overlap of A with respect to D, and you get all these values. Now what does 0, 0 means? There is no overlap between A and C. There is no overlap between A and D. Now what you do here is you will compare these IOU values and suppress the boxes with IOU less than the threshold. So what was our threshold? 0.5. So all these IOUs are less than 0.5. So all these boxes will be suppressed and you will be left over with only one bounding box called as A with confidence score as 90%. So these are the steps involved in non-maximum suppression where number of bounding boxes will be reduced to only 1. This is the visual representation where n number of bounding boxes got reduced to a single using non-maximum suppression. Hope you have understood. These are the three components. The fourth component, that is the evaluation matrix, we will do it in the next session. Thank you all.